Hello, good morning, good afternoon, everybody. Welcome to the next SimScale webinar entitled Energy Efficiency and Cooling Cost Reduction in Data Centers with Computational Fluid Dynamics. My name is Paweł Sosnowski. It's a great pleasure to be here with you. Before we begin, I would like to make sure that we are all properly set in the technical manner. So first of all, if you would be so kind to confirm that you can hear me and that you can see the screen with the title slide, please use your GoToMeeting application to raise your hand. Please raise your hands. I see some hands rising. That is great. I'll put them down right now. So I assume that everybody can hear me and we're ready to go with no further technical issues. Let's move to the webinar. A short word about myself. I'm Paweł Sosnowski. I'm the Customer Success Engineer here at SimScale. It's my pleasure to work with people who use SimScale professionally in order to help work with their simulations. I worked with computational fluid dynamics for most of my professional career. And yeah, it's my great pleasure to be here with you today and talk about this incredible topic. A brief overview of the agenda for today. We'll first have a very quick talk about the benefits of using CFD in general. We want to make sure that for those of you who have not used CFD or are not yet convinced that this is worth it, that I make a good case to start working with it. Then I'll give a short description about SimScale before we move to the topic of the day, that is the data center analysis and the cost reduction. During the presentation of the topic, I'll make a live presentation of SimScale platform, and with the live presentation done, we'll move to the results summary and discussion of the simulation results that we got for this particular analysis, and we'll close with a Q&A session. Before we begin, like last technical thing, I know that there might be some questions arising during the presentation, but since I get it from the experience that very often I tend to answer some of the questions few minutes into the presentation, I would kindly ask you to save your questions for the Q&A session. Of course, if there is something really unclear, feel free to post the question, raise your hand. And most importantly, if anything technically doesn't work or you suddenly lose the screen or my voice disappears and we're out of sync, definitely let me know. All right, without further ado, let's talk very briefly about the benefits of simulations. Why would we actually want to move from the standard engineering approaches, which has been working for us for a pretty long time? I mean, since the beginning of the Industrial Revolution, we were able to manufacture new products. And even with the new tools available, well, we are pretty successful and the civilization is moving forward. The big issue that we're facing when working with a traditional engineering approach is that it's not that efficient. We need to actually test our tools, our new products, before we release them to the general market in order to ensure that they are working the way that they are designed and that they are safe. Obviously, with the design process, we will be making mistakes. We're making assumptions. We will be testing them. In order to make sure that the gradual progress is achieved, we need to make multiple prototypes. And each prototype will cost us a significant amount of money, will take time to develop, and might actually result in draining the project before we reach the working conclusions or reach the working tool. The idea of introducing numerical simulations into the mix is to reduce the number of physical prototypes and perform numerical experiments that will verify that our design, our choice of implementation works fine. I'm using the term numerical experiment very deliberately. Actually, I don't like simulation that much, since when you think about simulation, it makes something, you think about something that is completely detached from a physical world. With the use of SimScale, with the use of CFD, and with use of finite element analysis, we are trying to mimic the reality as much as possible in order to get reliable results that can allow us to make accurate engineering decisions that will help us develop the product better. To be more specific, when we think about benefits for AEC industry, we think about a project that actually cannot be physically tested, at least in many cases. We could imagine building a little maquette of a building and testing wind loads or trying to see what happens when you put an HVAC system. But when you make a geometry that is much smaller and is scaled, you might lose a lot of significant effects that will be developing within the building while working with the ventilation systems or the wind loads. And, well, if you make a mistake in the engineering part and you build the building, you will face significant costs if you make a mistake. So our job will be to make numerical experiments that will verify that our assumptions about the building performance, about the ventilation, about the wind loads, about the energy efficiency are as close to reality as possible, and which will in effect allow us to make sound decisions and informated decisions on the engineering questions that are being brought to us while designing such a huge and complex problem. So that was a brief introduction to CAE in general. Let's move to a little talk about SimScale. What is it that makes us different from the others? Why use SimScale? Well, before we answer this question, we need to take a look how was simulation done so far. And in general, you would have a very skilled professional in your company or within your team who knows about simulations. You would acquire an extremely powerful computer for him, or you would rent it from an external vendor. On this computer, you would install a pretty expensive software with a single license, and you would do the work. The costs would be incredibly high, and the person himself would be, well, pretty isolated from the external work. The collaboration would not be that easy, and basically the progress of your project would not be that fast. With SimScale, we're bringing down the barriers that would stop you from using simulations in your daily basis engineering problems. You get a full packet of all application and all simulation capabilities, from structural mechanics, fluid mechanics, and thermodynamic simulations, all in one. Everything runs in the web browser. It's fast and easy to learn. You have real-time support from our engineers here. You're truly being one of the people who actually make this happening. And all that at a fraction of the price that comes with the traditional software. Collaboration with SimScale is extremely easy. You need to modify your simulation while you're traveling to China and then next day moving to Brazil, no problem. And all that being done through highly secure internet encrypted connections with data centers that are being monitored every day, all the time, making sure that your data and your projects, your intellectual property is safe, secure, and ready to be used anytime you want. So, which industry can use this kind of brilliant technology? And here at this point I have to share with you a little personal thing, because that's why I moved to the CFD in general. I wanted to be flexible. I wanted to be able to apply my knowledge to basically any industry in the world. And actually that is the case. You can run with industry problems from energy, automotive, aerospace, pumps, simulations, marine, machinery, whatever you want. Simulation will have its impact and will bring you benefits when working on your engineering projects. All right. I hope I didn't bore you too much with this short introduction and that you found it interesting. So we'll move to the topic of the day, because we're all waiting for that. That is how to answer the question, how to reduce the cooling costs of a data center using computational fluid dynamics. To move and forward and decide why should we actually answer this question and is it worth the look, we can take a look at this graph that represents the general importance of energy consumption within data center business and the interpolations. Note that this particular graph is a little bit outdated, I'll give you that, and it doesn't account for the blockchain revolution that is happening in the last years, which significantly increased the energy usage for data centers in general. So these curves that we are seeing here should be much steeper right now. But what we should take from this picture is that the amount of energy used for computational needs is growing almost exponentially or linearly. It's increasing very fast, and we will have to find a way to reduce these costs in order to make a sustainable business and a sustainable operation. When you take a look at the data center in general and the energy distribution or energy balance that is happening, what is the energy being used for? Significant part, about 50%, is being used for cooling. This is the piece of the pie that we are trying to optimize and improve. Today, we'll look at a general example of a data center that composes of 4 rows of server racks, 13 servers each, 13 racks each, composed into 4 columns, 4 rows, in a configuration that is called the cold aisle configuration, where the C-rack units will be introducing cold air through the plenum under the raised floor, and this cold air will be entering into an enclosed space between the server rows and later be heated up by the servers and exposed to the external part where there will be the returns sucking the air back into the C-rack units. To take a little closer look at the data center model that we have here, we will make several important simplifications for us to be able to actually approach this problem with computational fluid dynamics. First thing to note is that we will not model one-to-one the geometry itself. In this case, we are removing the perforated tiles that are put on the raised floor and allow the C-rack and access the air from the bottom plenum to the cold aisle, and we will replace them with a virtual model that will mimic their presence in a particular way. In a similar fashion, we will not exactly put every server with every little transistor, microprocessor, RAM, fan, heater, cable, and everything. We'll simply consider our servers as the source of energy that will be introducing heat into the air that is moving within the system. We're trying to address the problem from a macroscopic level. So the server heaters will be represented by a certain virtual volume that introduces heat into the air. To allow motion of this air, we'll again use another modeling technique, advanced modeling technique, that is, we'll introduce virtual momentum sources that will mimic the presence of the fans that will be taking the air away and out from the servers themselves. Obviously, any server room with any racks will have some physical protection of the servers themselves. They're not just standing out in the open. So we have also perforated plates or perforated walls and doors that close the server rooms. Again, in order to model one-to-one the geometry of such a door with a significant amount of perforations, it would be an insane task even for the strongest supercomputers that we're actually trying to model. In order to approach this problem, once more, we will use the physics and simplification and apply a virtual perforated plate that will stop the motion of the flow in a way that mimics the presence of such an object. And I will get to how to do that during the live presentation. Now, for the simulation setup and the design parameters of the system, overall, we will be introducing 208 kilowatts of total energy into the system, distributed equally throughout this 52 rack servers. The total area, the surface area of the data centers are 140 meters square, and we will be interested in the certain server intake temperature that is being put into the condition. The parameters that we can actually modify are the supply temperature that is being put into the servers, the flow rate that is being outsourced through the C racks, and what we'll be controlling is the rack cooling efficiency with the parameter RCI, which I'll explain in a moment. And in general, the idea will be to reduce the cooling cost function that we'll introduce towards the end of the presentation when we talk about the results. The parameter that is mostly interesting for us is the rack cooling index, which measures the cooling effectiveness of the system itself. We will have two parameters that allow us to calculate the performance of the tool and the performance of the server, like what is happening within it. We want to make sure that the operation conditions of the air that is being put into the servers is within a range between the RCI high and RCI low, which give the standardized limits for operation in such data centers. We will basically take an average of the server intake temperature that we obtain for every server within our system, and we'll calculate the RCH high and RCH low using the formulas above. We already have a standardized approach and standardized models of how should such a data center operate. I would refer you to the ASHRAE standards, which basically recommend the equipment intake to be within the range of 20 to 25 degrees centigrade. And they also specify an allowable range of operation for such servers between 15 and 32 degrees centigrade. So our job is to ensure that we are within these limits using the calculation that we have over here. Okay. In general, we wanted to perform a range of analysis and see different operational conditions. In this example study, we chose 4 different supply air temperatures that will be calculated and different supply flow rates of the air expressed in cubic meters per hour. So we will have from 80% to 140% of the flow rate supplied with different temperatures, which gives us 16 simulations and 16 numerical experiments that will be performed on this data center. Okay, we have an understanding of the task at hand. Let's take a look on how do we approach this and how do we do it live on SimScale platform. I already took the liberty to open the project. I believe that later on my colleagues will also share this project, so this will be a part of the public project library available for everybody to use as an example and a starting point for their own analysis. We start with the CAD that was directly uploaded to SimScale in the step format, and we can investigate it in some detail. Notice that the servers are right now represented only by those hollow spaces, and we will be introducing all the elements such as perforated plates, momentum sources, and the heating elements within the simulation itself. And we'll jump to that in a second. So we have the geometry ready, and we're ready to mesh it with SimScale. In general, this is a pretty simple operation. If your geometry is a typical thing that you want to work with, you can either use the automatic SimScale approach, which we're developing every day to make sure that your projects are working, or you can go with a parametric approach. We provide a lot of trainings and a lot of materials on how to make the meshing work. In the end, for many projects, meshing takes 80% of the time to get the working mesh. Fortunately for this geometry, we made sure that the model is not complicated very much, and we will be using advanced modeling techniques that will mimic the presence of the more complex elements within the system. So we end up with a mesh that is around 7.7 million elements, which is a relatively high, relatively big mesh. With this ready, we can go and set up a simulation. And here is a highlight of one of the biggest strengths on SimScale platform. Any type of simulation that you want to perform will have a very similar workflow required from you in order to set up your analysis. Let's say that I would like to run an incompressible flow simulation. I'll create a new one, and all I have to do right now is to wait for it to load. That's number one. With a reasonable internet connection, it happens almost instantaneously. And from what happens is that on the right side in the navigator panel, you'll get a tree view of the properties. And all you have to do is go from top to the bottom of your simulation setup tree and apply conditions and settings in a consistent way that will represent this numerical analysis you want to perform. Of course, we already did that for the analysis of this nice data center. So the first big task that we needed to do is to create the virtual objects that will represent the elements, such as some grills. I see that there is quite a lot of these objects. Let me do one more thing. I'll hide some of them. So right now we have some grills being displayed. I see that there are some artifacts from different objects that are not being used in the simulation itself, just to position them properly. But basically what we do is we create all these elements that later will be representing the virtual objects that we will be assigning as elements of the simulation, such as the doors, the momentum sources. So we have the fans, for example. Let me just hide these guys here. There we have another box that represents the fans of this particular aisle of servers. And of course the heating sources, each one of them positioned properly in the system itself. Note that right now all these elements that I'm showing you, these are simply a virtual boxes. They are not linked to anything. We're just creating what's called a geometry primitive. With that ready, I move forward or downward within the list and start setting up simulations, like, for example, gravity. One thing that many people tend to forget. I used to do this a lot. And one question that I always get is, why do we have to set up gravity? It's always pointing downwards. Well, an obvious answer is that sometimes people decide that Z minus is downwards and sometimes it's Y minus. I recall once running a simulation of air convection within a room where gravity was pointing in an X positive direction, and I misplaced that. The results were pretty interesting, let's put it that way. So we move forward, applying the materials such as air. Very often we get questions that people who are getting a little afraid of the huge amount of parameters that you have to supply. We are coming in front of this, providing a small material library that allows you to select some basic standardized materials for your analysis. Obviously, if you want to use different material properties, you can modify these and use them for your flow. Moving forward, we have some initial conditions. Since we are running a steady-state simulation, this is not that important, but what will be important is the inlet conditions that define how much air is being pushed from the C-rack units into the bottom plenum, the outlet conditions, and the walls, which will be considered to be adiabatic and not influencing the flow at the very beginning. And I clicked on them. This needs to take some time before it loads all the faces and highlights them. So I see that there was a question actually. Are the fan momentum sources applied as surface boundary conditions? No, this is where we're moving to answer this question. In order to apply momentum sources, we go to advanced concepts of your simulation. Over here, we have 4 categories that are right now available. We have rotating zones, which we'll not be covering today. We have porous medium that are used with porosity models, such as Dial C4-Heimer model, to define the way that our virtual plates work. So let me just show these guys. There's quite a lot of things here in this simulation. It's a very nice one. So there we go. We have the perforated plates that will represent the presence of the objects that are connecting between the cold aisles and the plenum. We have then some racks that we already said that are blocking the entrance and exits from our servers. After that, we have the heat sources. This is the place where we are actually applying energy into the system and supplying energy to the system. So the air that is positioned within these boxes that I'm highlighting right now is given 52,000 watts of energy each, which sums up to the value that we desire, that is the 208 watts. Now, when it comes to the momentum sources, it's extremely easy. Once again, we need to have the defined geometry primitives, and we simply give the average velocity that is supposed to be achieved within this domain. So let's show, for example, one of these fan elements. And notice that in this case, we need to make sure that we properly define the direction of the flow. Since this is a vector, we want to have half a meter per second being introduced into the domain, negative, and the positive direction of the flow. So let's show these guys also. So we have the fans that are sucking out air from the aisle to the exterior and the main room. All right. After defining the advanced concepts and making things ready, we move forward, ending up in the numeric section, which is the most scary part for many people who start with their simulations. But this is where the power of SimScale shines. Whenever you have a simulation, first what you do is you start with the default configuration that in general is defined in such a way that should apply to most of the problems you're dealing with. If it happens that your simulation does not converge or you have trouble with numerics, all you have to do is look for a similar project that has already been published by other users and mimic their numerical settings within your project. Or you just talk with us and we'll be very happy to help. As one of the last steps, we are ready to set up simulation control. This is where we decide how long should the simulation run. And what is very important, we choose how big a machine should perform the calculation. On SimScale, you get access to machines ranging from 1 computing core to 96 computing cores right now. And you can run any number of simulations simultaneously on any number of cores. So in our example over here, all the 16 variants of this simulation were running simultaneously using 16 times 96 cores to perform the calculation. And thanks to that, within around 2 hours, or let's say 3 hours to be safe, we already had all the results ready on our desk, being ready to be processed. SimScale also gives you ability to visualize your results online, to have the first peek look into what's going on in your system. Let me give you an example. I'm jumping to the post-processor section. This is the third step in the simulation process. I already took the liberty to load one of the cases. Since they are pretty big, it might take a second for them to load. So I prepared it in advance. Of course, performing numerical simulations and analyzing the data that we acquire from them is out of itself. This is the way that we are going to make sure that we actually can take an engineering decision that is meaningful. So obviously we would need to analyze the data in a proper way, and this is just a demonstration. Excuse me. So I'll just show you a single slice, this time as a sneak preview of the temperature profile at 1 meter per second inside our data center. We can clearly see the presence of the cold aisle. Let me just show the temperature. Okay, this is really nice. And we'll reset the view very nicely. Obviously, we can create snapshots. We can use some more complicated visualization techniques. This is one of the screenshots that was taken in advance, which demonstrates streamlines or the flow pattern within the system itself. Okay. Since we don't have much time, I'll move to the next section, that is the results summary, and what did we actually obtain by running all these 16 simulations. Let's first take a look at some results. This is, again, since we are having a limited amount of time and we had 16 cases, I'll focus on a single simulation that was running at 120% of the flow rate capacity and 16 degrees centigrade inserted into the bottom plenum through C-rack units. The results look pretty similar for all the cases, but this one was chosen just to make the post-processing as an example. Note, so we have right now the server intake temperatures taken at the slices. We can immediately see the difference in temperature that is present for all the different servers themselves. If we were to take average values for each square that is present in this picture, we would see a graph like this, which gives us an understanding of how does the data center perform. Some more visualization. This is a cut through the middle of the server rack, rows number 1 and 2, and some more cuts through the back back aisle. Notice that we are generating heat. Inside these setup units. So there is right now we are looking at the velocity plots with some streamlines and with some LIC representation of the vortexes, plus visualization of the flow direction. You can see that the velocity is significantly higher. It is the most of the velocity is being pushed through the fans or the virtual fans that we introduced into our system. A picture, another take on the temperature profile, and some side cuts to visualize the cold aisle regions where we have air being pushed into the aisle from the plenum and being distributed through the servers themselves. The heat generation and the introduction of the temperature and heat into the air as being blown. Notice the interesting effect that because we are pushing the air from the plenum and it's moving with this big jet effect, the bottom servers are subject to worse cooling, and they might get higher temperatures. Last but not least, let's take a look at the pressure drop at perforated plates and grills. So since we are introducing a virtual objects, one would expect that the pressure drop would not look smooth, and that's exactly the case. We have a significant pressure drop at the bottom perforated plates and at the sides. If you notice these little jumps on the top of the server rack rooms. There was an interesting point that was asked. The 3 hours of computation, or the 3-hour time, is the physical time that you actually used to wait for the results. In the end, if you were to run these simulations on a single machine, like your laptop or a PC, you would need to run 16 times 96, because you have 96 cores, and times 96 times 3, because this is the 3 hours. So we are modeling, in this case, these are steady state simulations that we provided here. Of course, you can run also transient analysis on SimScale, but most importantly, this is actually the physical time that we as users had to wait while the computers were grinding a lot of what we call core hours, which was 96 times 3 times 16, since we had 16 cases. All right, so we have the results. We can calculate the values of the performance for every case, and now let's decide which one is best. What we'll take is the cost function definition, which will say that the chiller, which is included inside our C-rack unit, will perform better and allow better evaporation within the unit if the temperature that is supplied is higher. This is a little contradictory thing. I was also interested to find this out. And the second thing, obviously, the faster our fans are operating, the more we have to pay for the energy that is used to operate these guys. So, using the formulas that I introduced a little earlier, we are able to calculate the RCI high and RCI low coefficients, which give us the best operation conditions, or the scale of the operation conditions for the system. And when it comes to the RCI high unit, we notice that basically all the operation conditions with the low temperatures are working fine for us, and we could choose any one of them, except for the low volume air supply. That is the 21 degrees, 80 and 100. They are not above 95%, not above 95, which is the desired criterion. On the opposite side, when we look at the RC low operation conditions, only the simulation, which had the supply temperature of 21 degrees centigrade, would match the criterion itself. If you overlap the RC high and RC low coefficients, we find out that there are only two possibilities that would match the requirements. That is the air supply at 120% or 140% at 21 degrees centigrade. Now, as a final step, we have a base calculation of the operation for a data center. And we know from experiments or from a data center disclosure that the cost of operating at 100% air supply rate with 13 degrees centigrade introduced as a supply air, we would pay around $33,000. Whereas if we were to switch to the conditions that we just calculated, we would be able to save 11% of this sum on the operation. So increase the fan speed and increase the supply air temperature. Okay, we are getting to the end, and I'm sure that all of you are eager to start your own simulations and start your own analysis. It is an extremely easy thing to do. All you have to do is go to simscale.com, create a new project, create an account. The basic accounts are completely for free. You can upload your CAD model, start a simulation setup, use the examples that we already have in our public library, run the analysis, and make design decisions that will improve your products and make your engineering process more efficient. All right. We already had 2 questions throughout the session. I would be very happy to open the board for more questions that might be there. One small request, since it might take some time for you to type, and I wouldn't like to go away or stop the presentation without you being able to pose your question. When you start typing, please raise your hand so that I know that there is a question incoming, and I will be very happy to wait and answer before you are able to pose the question. All right. There is already a first question. Is it possible to simulate the servers as they are? So if I understand correctly, you mean all the components. Yes, this is definitely possible, but at the same time, this whole depends on the scale of simulation that you want to perform. If you are working with a full data center, in order to capture every transistor, every little element that is posed inside such a domain, you would need an incredibly fine mesh. And this might simply be too much for even a supercomputer that is built in this data center. What you would do instead is actually run a simulation of a single server, like the one that we have here in the electronics cooling example. Take an understanding from there. How does it perform? How much heat is it introducing into the air? And then use it to model the virtual server that is positioned in our data centers. Here's another question. Simulation results are very sensitive to correct inputs. That is very true. Have we validated the software against real examples? And yes, we are doing whatever we can to validate and make sure that the simulations that we are working with are correct. So if you go to our help section and the documentation, you can take a look at the validation cases section, where we have multiple different analysis types validated against numerical experiments and against scientific papers. At the same time, I have to put a disclosure here. The software itself works fine, and it produces valid results, supposed that the user uses it properly, meaning that he uses the proper technique and uses enough mesh refinements and so on and so forth. We are doing whatever we can to enable users to do that, share the knowledge. That's why you have the public projects and examples. But obviously, if I were to sit in a Formula One car and drive on the track, well, I would make a lap, but I wouldn't beat the record. In a similar way, once you have a working tool that is very good at what it does, it definitely will perform, but at the same time, it's good to know how to change the gears and move with your car forward. Another question, can you insert different cooling units? So comparable into in-row units or others. In general, you will have to define the model that represents the cooling unit itself. In this case, the analysis that we're doing here, the cooling unit is represented simply by a box that has an inlet and an outlet. Let me just show you what I mean by that. So I will just hide these surfaces over here so they block. So these are our C-rack units, and basically these are hollow boxes with two faces that we decide that one of them will be the inlet, the one that I'm flashing right now, and the second one will be the outlet, or the other way around. The top one is taking the air away from the system, and the bottom one is pushing the air into the plenum. So if you decide that you want to have an inlet, what you do is you decide what is the flow rate that is supposed to be going through, or velocity, and what is the temperature that it introduces. We're considering this object to be a black box right now. How do you, then our next question, how do you account for the airflow performance curves of the internal fans in the IT equipment? So right now, with this, well, this is very simple. I would relate this to the question that was posed earlier about these details of the object. So what I would do is I would first run a simulation of, why is it? To reload this, sorry. I would first run a simulation of the IT equipment itself, or have an understanding of how would it perform, and then we would use it to model it as a black box, or this virtual sphere that we have here, or virtual box for the IT equipment. And when it comes to the performance curves, there are other modeling ways where basically you can use objects to have fan curves as inlets and outlets, and that will adjust depending on the flow performance. But there is a certain limit that you can work with, you can do with the software. If the next thing, if I well understood, one of the main hypotheses is the cooling efficiency of the rack, the ratio. Do these values come from measurement of the racks? So yes, for this particular study, we had a reference paper that we used to get the performance curves and calculate the performance of the system itself. So there is if you have a raised floor with a fan and heat exchanger, so we have the raised floor over here. This is exactly the thing. This is exactly the case. Now the question would be, where do you have your fan? There are multiple ways in which you can model the presence of a fan. You can either use the approach that we have in this case, where we introduced a virtual box that represents the presence of the fan itself, and then we are adding a so-called momentum source. But you can also upload the geometry that will represent the fan itself. You can even have a multi-reference frames, so MRF modeling of the flow that is being generated. So, but when it comes to the heat exchanger, this whole comes down to the scale of the problem that you want to simulate. If we were to simulate the C-rack, this would be, I would say, one big simulation to perform on its own. If we're interested in the performance of the whole data center, usually we change the scale of the problem and we make required simplifications. Is it possible to upload a geometry from a BIM software as Revit? Yes, we support multiple formats, and we are extending the range and the list of software that we support. At this moment, let me just quickly show you the list of file formats that we are supporting. Still, if possible, use the step format if you have any other software that doesn't work. This is a standardized geometry type, but we also support SolidWorks, Autodesk Inventor, PowerSolid, Rhino, and ACIS. So, yeah. And there are more to come. Okay. On top of that, if you are interested in working with your CAD online, you can import your geometries directly from Onshape, who is our partner. This is the online CAD tool. The guys who found this were the founders of SolidWorks. They're making a great business case right now, moving CAD to the next generation, the next century. So highly encourage you to do that and test it also. Okay. Another question, is it possible to add objects or add CAD, add racks? Am I reading it right? Add C-rack types. So I guess what you're referring to is simply adding standardized equipment into your geometry. At this moment, what you have to do is model the object as a CAD element and represent it within your CAD. In this case, we have a volume extract of the domain, or let me just go to this example. I think in the electronics cooling example, it's seen out better. Yes. So in this case, let's say that this is our data center, a very small data center. We would have the air domain, which I just hid, and we would have some standardized equipment. That is some transistor, we have some more elements and some resistor. But the thing is that these are just geometrical representations of these objects. We will have to mesh them, and then inside the simulation designer, you would have to define what is the inlet velocity, what is the outlet, what is the heat that is being generated by this object. So there are a few more steps when it comes to defining such elements and putting them into the simulation. Okay, can I download my results and post-process them offline? Yes, you can, of course. All the results that you have on SimScale are available for you to be downloaded and processed with any software that works with the formats that we're supporting. In the background, we're running OpenFOAM with some modifications and improvements that we make sure that it actually works as it's supposed to. So you can get a free software called ParaView, which is also used as a basic engine for the post-processing right now, and then use it to process your results and make some incredible images. Actually, all the visualization used in this presentation, or most of it, was done with this tool, which is open source, free of charge, and pretty straightforward to work with. Okay. Can I add rotating fans into my simulation? So this is a very interesting question. And there are two ways to approach this. You could use either the first answer. If you want to really rotate your fan, you would need to run a transient simulation, and you would need to use a specific rotating region called AMI, arbitrary mesh interface. This is a very computationally intensive type of simulation, and actually I would leave it as a last resort if the simpler modeling techniques don't work. The second approach is to use the multi-reference frame simulation, where we'll be introducing momentum sources or rotating momentum sources like Coriolis force and centrifugal force into a virtual region within the simulation setup. We have very interesting tutorials online regarding that, and with that you could definitely add rotating fans or model presence of rotating fans inside your geometry. Okay, that was the last question. So it was a great pleasure. Thank you very much. I really hope that you enjoyed this introduction webinar on the ways on how to use CFD to increase the efficiency and reduce the cost of operations for data centers. On behalf of the SimScale team, thank you very much for participating, and I really do hope to see you with the simulations, doing your simulations on the platform. Have a great evening. Paweł Sosnowski signing out. Bye-bye.